Good morning. Hope you had a nice holiday. Let's jump back into some maths, eh? Which is more fun than probably whatever you did on your holidays. We're looking at similar shapes and congruent shapes to start with. I'd say similar shapes is probably more of an important topic within maths, but because there's a bit more complexity to it, congruent shapes is just kind of one thing to know, but it's important we see these two together because it's pretty easy to confuse the two, and we don't want to be doing that. So, starting with congruent shapes. Congruent shapes is shapes that are exactly the same, but they could be rotated. So they could be rotated. So let's look for some shapes that are exactly the same. We've got a nice L shape here, and we've also got a nice L shape here. So we can say our congruent shapes are A and G. And looking for something else, we've got a bit of a tetris shape here, and a bit of a tetris shape here. So D and I are congruent, they're just spun round versions of each other. When we talk about similar shapes, it's not that they're exactly the same. In a basic sense, we're looking for shapes that are enlargements of each other. Maybe enlargement doesn't have an E there, I'm not sure. We're looking for shapes that are enlargements of each other, and enlargements could be bigger, they can be smaller as well if you have an enlargement of a decimal scale factor. So, having a look at this. So, I kind of know the answer already because I've done these questions, but we've got a length of 2 here, and a length of 1. So we're looking for another rectangle, really, that's going to seem like it's scaled up by the same amount. So, a width of 2 and a height of 4. Can we see that we're timesing by 2 and we're timesing by 2? So this has been enlarged by a scale factor of 2. So I'm going to say my similar shapes here are B and F, and they've got a scale factor of 2. Okay, let's have a look at another example. So maybe you want to have a quick look at this one, see if you can find a similar pair and a congruent pair, and come back to the video when you've got them. Okay, so first let's go for our similar pair. Looking for two shapes that kind of look like they're the same shape, but one's larger than the other. I can see nice and clearly that I've got two right angle triangles here. We've got a length of 2 by 2 and a length of 4 by 4. So we can see it again. We'd have a scale factor of 2. Isn't always going to be the case. Sometimes I'm going to abbreviate scale factor as SF. Don't get that confused with significant figures. I'm not meaning that pretty much any time today. And then congruent, two things that are exactly the same. Well, we're close with E and C, but we've got a length of 4 and a length of 3, so not them. Here we've got a length of 3, length of 3. If we know our Pythagoras well, we should know that a length of 4 and a length of 3, that's going to make this a length of 5, because 4 squared plus 3 squared, then all rooted. And then we would have two lengths here that are the same. We've got a 3 and a 1, and a 3 and a 1. We would make it root 10. I'm just going to denote it by a little fish symbol to show that these are the same. So we've got all three lengths exactly the same, which is what we're looking for. So D and G are our congruent pair. There are other ways of spotting shapes as similar. Obviously, we're not always going to be given shapes with a square grid behind it, and we're not always going to be given the measurements of shapes. But we are going to be asked to find if shapes are similar. That's going to be something for another video. But there's three kind of proofs, if you want to call them that. to show two shapes are similar. But like I say, that will come at another time for another lesson. Having a quick look at these three little questions, maybe you just want to have another go yourself. Very quickly, they shouldn't take you too long, and just have a think about these. So it's true, false, or sometimes true, sometimes false. Okay. If triangle A is isosceles, triangle B has to be isosceles. That's saying if we've got two similar angles, triangle B also has to have two similar angles. Well, if you think about enlarging a shape, we've got an angle there. When we find a similar shape, it's either going to be smaller or larger. If we just make this shape larger, is there anything happening to that angle? No, because it's literally that first tiny bit is the only bit that actually creates the angle. The rest of the lines make no difference to it. And you can think about that for all the other angles in the shape. And we would see that in fact we always have the same angles within similar shapes. So the lengths change, but the angles always stay the same. So kind of phrasing that, say angles remain same in a similar shape. So we've just shown that that one's false. They have different size angles. Nope, they stay the same. And triangle A has a larger area than triangle B. Well, we've got two similar triangles like this. Yes, one of them is going to have a larger area because we're making it bigger, or we're making one smaller. But there's no saying what we call it. I mean, that could be A, and that could be B, or this could be A, and this could be B. So this will be a maybe. Sometimes it's true, sometimes it's not. It depends how you label your shapes, or how your shapes are labelled. There's no meaning that lower letter in the alphabet means smaller shape. Okay, having a go at some actual questions. So, finding a missing side, there's a couple steps I always like to go for this. So, my first step would be to draw the shapes out like they've done here. So you probably see on this question, they've drawn them out so all the angles are in the same position. Whereas this one, the shape's been rotated a bit, so when I get onto this question, I'm going to be drawing them out to make them look in the same orientation. So where the angles are in the same positions, it makes it a lot easier to link up your sides. So my first step would be to redraw if needed. My second step is to find a pair of sides. What I mean by that is lengths on both of the shapes that we have. So I've got this length here between the single and the double angle, and I also have that length there between the single and the double angle. So that's going to help us find our scale factor. And what I mean by scale factor, if we don't know that already, it's what we're multiplying by or dividing by to get from one shape to the other. So we can easily see in this example the scale factor would be 2 because we are doubling the shape's lengths to get to our new shape. The way I kind of like to find a scale factor, we're not always going to get easy numbers like this. I do my large length divided by my small length. So in this case would be 10 divided by 5, which gives us 2. So it's exactly what we expected. But that's a nice way of finding it when it's harder numbers. And then step 4, well, when I'm going from this shape to this shape, it's clear I'm expecting larger lengths. So I'm going to times by my scale factor. And again here, I'm going to times by my scale factor. I'll fill in that 0.4 in a bit when we get this next question done. So, I've got my large triangle here. I'm going to draw it out in this orientation. So triple down there, single and double. So 10, 5, blank. And then I've got my small triangle there, looking the same, different size. And I need to find what these lengths are actually kind of linking to. So between the triple and the double angle, I'm going to have 6. So there we go. Between the single and the double angle, I'm going to have 4. And then between the single and the triple, I'm going to have a blank that I need to figure out. So we can see now it's really easy to do our second step, finding the pair. So 4 and 10. So my scale factor is going to be large divided by small, which is 2.5. So to get from 6 to what my missing number here is, with it being the same side on our new shape, well, we're going from our small shape to our large shape. So I want to times by my scale factor. So 6 times by 2.5 is going to be 15 centimeters. And to get from my large shape to my small shape, it would make sense for my answer to be smaller, because I'm going from a larger shape to a smaller shape. So in this case, I'm going to divide by my scale factor. We can see we're doing a bit of inverse. Times, divide, times, divide. So when I do 5 divided by 2.5, that will give me 2 centimeters. So I'm going to fill them in here. So filling in our fourth step, large to small shape, we want to divide by our scale factor. And small to large shape, we want to times by our scale factor. Okay, I've got 3 questions on the next slide for you to have a go at, which are here. So pause this, have a go at these, and then I'm going to pop some solutions on the next slide for you. Okay. So, hopefully you've had a nice go at them. These are our solutions. So, if I zoom out a little bit, I can get all 3 on for you. Perfect. So have a quick look through them. We should get our answers. I've put them in nicely here. One key point I've made about this is, because I've got 2 things on this shape, when I've rotated the shape, I've linked up which boxes were which. So when I'm filling in my final answer, I don't put 6 there and 7.5 there by accident. I didn't have to do it on this shape because there was only 1 on each shape, so it made it quite easy. But this one could have been a little bit more difficult if I didn't label up what boxes, which unknowns were which. And then just showing when 2 things aren't similar. You just want to show that they don't have the same scale factor for each length, because that's the property of a similar shape. It should be every length should times by the same thing, and I've shown here that they don't. Okay. Looking at contained triangles here. So what I mean by contained triangles is just triangles within themselves. So you can see here that I've got a large triangle around the edge, and then a smaller triangle here. I'll make that pen a bit smaller and I'll draw that on again. And a smaller triangle there. So my small triangle, I'll try and keep it color coded, would be 9, 7.5 and 6. And then my large triangle, this is where it's really important to draw it out again. So this would be, well, 7.5 plus something. This would be 9 plus something, and this would be 8. The reason I've got 7.5 plus something is 7.5 plus something, 9 plus something. Then we've got 8. Well, our similar pair here is these bottom lengths. So to find my scale factor, I'm going to do 8 divided by 6, which gets me 5 over 3, or if you want to visualize it as a number, 1.6 recurring. So, going this way, this is small, this is large. I want to times by 5 over 3. So 9 times by 5 over 3 is going to give me 15. I'm going to put that below in a bracket. Because 15 isn't our final answer. Our final answer would be 6, because 9 plus 6 gets me to 15. And then 7.5 times by 5 over 3. That's not one I think I can do as easily in my head. So I'll do it on a calculator. That's going to get me 12.5. Again, I'll put that in brackets just above. 12.5 isn't going to be my final answer, it's going to be 5, because 7.5 plus 5 gives me 12.5. And this final one. So, this is my triangle up here. And my large triangle in red. So let's have a look at some of these lengths. We've got 10 plus something, 9. My lengths here would be 6, 8 and 10. So my pair that I'm going to be working with to find my scale factor is here. So the scale factor is going to be 9 over 6, which is 1.5. So 8 times by 1.5 gives me 12, so 12 is going to be my length here. And 10 times 1.5 is going to be 15, but 15 isn't our final answer is 5. Because 10 plus 5 gives me 15. Okay, so I've got a question for you to have a go about, a bit of a real life one. And I'm going to put the solution up on the next slide for you, so give it a pause. Okay, hopefully I had a good go at that. I'll do a bit of a zoom out to get this all on. This guy is ginormous, 2.7 meters at his shoulder, must be about 3 meters tall, but hey ho, it was a randomly made up question. So 2.7 meters you should have got for your final answer, and this is the working out I did to get it. Okay, and then final thing, we're going to do a tough example. You'll see why this gets tough. You might think from the outset, oh, this is easy, but if you pause it and have a go at it yourself now, you might get stuck at a certain point. And we just need an extra bit of thinking to have a go at this. So, as normal, drawing out both our shapes. Nothing different ever changes with that. Filling in what we know. So blank, 6 blank 3, 6 plus blank, blank plus 3, and 5. So yes, we can find our scale factor nice and easily. That's going to be 5 over 3, or again, we know it's a 1.6 recurring. If you want to visualize it as a number, sometimes it's a bit easier. So let's find this. 6 times by 5 over 3. 6 times by 5 over 3 is going to give me 10. So we know that my missing value here is going to be 4. That's just like before. However, we've never had it where there's been an unknown on both. We don't know what to times to get this, we don't know what to divide to get this. So the way I might look at this, oops, let me make that pen smaller. I'm going to put an X in there, because we know that them boxes are going to be the same. They both represent this line. And if I times this by 5 over 3, I get to my new length. So let's form an equation. So if we form an equation, x times by 5 over 3 equals to x plus 3. That's all we've been doing for the ones before. 6 times by 5 over 3 gives me 10. So we could have written out an equation like this and solved it. So we've got 5 over 3x equals x plus 3. I'm going to go to here. Let's times by 3 to both sides to get rid of this fraction. So I'm going to have 5x equals to 3x plus 9. Then going to take 3x from both sides. So 2x equals to 9. Then I'm going to divide by 2. So x equals to 4.5. So we know here is 4.5, and we know here is 4.5. We don't have to do any subtracting this time. Always take a step back when you get your answer and think, is that straight away my answer, or do I need to do something with this 3? In fact, we set up x to be this short length, so this is just 4.5 here. We don't need to do any subtracting like we did for this this example here. Okay, question for you to have a go at, then I'm going to pop the solution up and then we'll be done. So, there you go. I'll give it a pause. Have a go at that one, please. Okay, hopefully we had a good go at that. And our solution is here. So we should get 1.6 and 2 if you got that well done. This is my working out for it. So I drew out my large triangle, my small triangle, found my pair, found the scale factor of 2.5 or 5 over 2. And then it was fine to find this. This was just a straight multiply from 0.8 times by 2.5. However, I'd set some algebra up for this, x and 2.4 plus x. Did my working out down here, and I solved this to be 1.6 centimeters. Okay, hopefully this video was helpful for you, and I will see you next time.